I think I understand what the person's trying to get across. But there are times where I really cannot tell. So try to make it easier on my grading. Just do it perfectly. Grading is really simple. Let this be the first class that does that. Oh, I'll be bragging about you for decades if you pull that off. Questions before we do? Yeah, box on ground. So first thing I do is draw the picture of what's going on. Draw it less slanted there. And I'm just going to the top one is box 1 and the bottom one's box 2. If you don't like 1 and 2, A and B, alpha, beta, A and P, or whatever. What's the first step? I think that was said. Now, I don't have to draw them in the order in which they're actually in the problem. Personally, I find it a whole lot easier to draw them in the same relative order as best as I can as in the problem. There are cases where it gets a little bit difficult, especially when we get to the test level problems. And it has caused some confusion to students, and I'll talk about that when we get there, which will probably be next Monday. We have our checklist. Anything we can eliminate? Okay. And others eliminated. Why?
Because there's not like an unknown source that's pushing on something.
All right, we have the same two forces as before, or the same two type forces as before. Let's do weight, because I still think weight's the easiest. Which way is weight acting on which object?
Weight is acting on both boxes. First one onto the second one.
Wait, I'm drawing this arrow which way?
Down.
Down, okay.
And then the second box to the ground.
Like that?
Mm-hmm.
So far, so good.
And then another arrow down on the ground, like down on the ground.
Why down?
Because it's on the ground.
Are you talking about the,
Like on
what type of force is this down on the ground?
the other box is pushing it down on the ground.
What force is that?
Oh, it's up, I'm sorry.
Up on the ground. Well, what force is this? It's either weight or normal force. That's what I'm asking.
Okay, I'm sorry, it's weight.
Okay, so weight acting up on the ground?
Yes.
Okay. So far, so good. We're not done yet.
Would also be weight acting up on the second box?
Ooh, another rookie mistake.
Oh, no.
Thank you for bringing it up though, because I wanted to emphasize, no, not. Because weight required, if the weight is acting up on the second box, presumably you're pairing it with this one.
Yeah.
That means if the second box disappeared, this thing would just hover. If the second box disappeared, that's falling. So that the other part of this weight is not with the second box.
Is it also on the ground?
We have two acting up on the ground. Not done yet. There's a reason I do box on the ground. Do box 1 and box 2 weigh the exact same thing? All right. So if they don't weigh the same thing, why are we using the exact same symbol for it? We need to differentiate because these weights are not the same. And we do that with subscripts. I can put a little 1 right there, and I'll put a little 2 right there. I'm putting a 1 right here because, well, that's box 1. 2 because of the 2 right there. There are some students who, they put all their weights down and then they just start on the left side and they do 1, 2, 3, and they just number them straight across. I can follow it. To me, it's a little bit simpler in my mind if the subscript has something to do with the object. So this weight 1 here is being pulled down towards the ground. This pulling up on the ground. So I put a little subscript 1 there and a subscript 2 here. Or I could have, flipped the subscripts since these are sort of generic up on the ground. But you do need to have the subscripts if I have more than 1. I will have other students who will skip the subscripts completely in the complex diagram. And the way I deal with that is I give them full credit for one of them, one of the pairs, and then all the rest they get a deduction because they are not the same. All right, so we have 2 small objects, so we've dealt with, and 2 weights there, so weight is done. Normal force. Normal force between what and what?
Ground in box 2.
Ground in box 2?
Mm-hmm.
Which way is it acting on which one?
We'll go box 2, we'll go.
Is it up on
we'll
2?
act up on box 2,
So why is it 2?
and then down on the ground.
Is it 2? And? Are we done?
No.
Up on box 1?
Down on box 2.
Yep. Normal force requires contact. Box 1 is not touching the earth. There is no normal force between box and ground. 1 and 2 are touching. Therefore, oh, mistake there. That should be a y sub 1 there, down on box 2. If your older sibling is sitting on top of you, not that I haven't gotten over those scars. If your older sibling is sitting on top of you, that's what you're feeling right there. You don't feel their weight directly, you feel this normal force. If all you were feeling was their weight, then if they were bouncing on you, hypothetically speaking, you wouldn't feel any different. It's the normal force. All right, so questions on this before I actually talk about an actual application? All right, actual application. You're standing on the bathroom scale. And we'll call this the ground. If we did a force diagram, we have the person there, we have the scale, and we have the ground. Force diagram looks exactly what we just did. I'm going to change the subscripts because we now have something other than box 1 and box 2. And I don't think yellow's going to show up. Try brown. So there's a weight acting down on the person. That is horrible. So we have weight of person acting down and weight of person acting up on the ground. We have weight of scale acting down and weight of scale acting up. Put a little flare in the W's, all right. We have a normal force up on the scale from the earth, so normal force on scale and normal force on scale. And then there's a normal force between the person and the scale. Normal force of person. normal force of person. I hope that you can see the parallel between this and that. The only thing that's different is that I've changed the subscripts to reflect a different physical problem, but the force diagram should look identical. Questions to here? All right, so here's the question. You stand on a scale. What does the scale actually measure?
Your weight. Oh, well,
If you look at the forces acting on the scale, your weight is not on here at all. You have weight here acting down on you. You have weight here acting up on the earth. Your weight is not acting on the scale.
Gravity?
You said gravity? So let me, this came up earlier, the word gravity was used earlier. Gravity is a huge topic. There are many aspects to gravity. There's the force due to gravity, or weight in a lot of cases. There's acceleration due to gravity, there's this curvature of space and time due to gravity, but gravity itself is a really huge category, and so that's the nitpick that we'll do throughout the course. So if you meant the force due to gravity, or weight, same situation is the force due to gravity acting, your weight is not acting on the scale, it's acting on the earth and on you. Is the scale reacting to you when you stand on it? You got one person who's acknowledging yes. When you stand on the scale, does it know that you exist? Not philosophically, just that it will do something when you stand on it. So therefore, it's being influenced by you. What force are you exerting on the scale? Look at the force diagram. What force are you exerting on the scale?
Normal force?
Yep. That is what the scale is measuring. See if I have it here or if I took it home. A scale. Can you believe it? My brother didn't want this. It's part of my inheritance. All right. So as I stand on it, it is way off because it says I weigh about 160 pounds. All right. If this actually were measuring my weight, there's an easy way for me to lose weight. All I have to do is, if I do that, the thing goes down near zero, then it shoots up to maybe 300. So huge weight gain followed by huge weight loss. There we go. My weight is actually not changing. The gravitational pull between the Earth and me is not changing significantly. Now, why do we say that is your weight? When it's not actually measuring your weight directly. How is it measuring your weight? If an object is in equilibrium, the total force is equal, total force equals 0. I know it's about time to go, but I want to connect this up with something we did earlier. If I am in equilibrium here, as I stand on the scale, that means the total force acting on me is 0. Well, I have two forces here. If my total force is 0, that means that when I add them head to tail, I should end up back where I started. So I have this normal force of P acting up on me, so now I have a new starting point. I'm going to add to it my weight. If I'm in equilibrium, then I have just as much force acting up as down. So the magnitude of my weight and the magnitude of my normal force, badly worded, the magnitude of the weight on my weight is the same magnitude as the normal force the scale's pushing up on me. And so the magnitudes are the same, and therefore this magnitude of this force right here has the same magnitude as my weight, and that's why we say it's measuring our weight. If they add up together and don't end up back where we started, so if I have YP going that way, and so YP is bigger but weight hasn't changed, my net force is up, because I started here and so there's my net force, there's my resultant. That means I'm accelerating upwards. If my normal force is smaller than my weight, so that suddenly changed Coulomb convention there. So weight, roughly the same thing. If the normal force is smaller, then my resultant now is there's my resultant. The net force is downwards acting on me, and so I'm accelerating downwards. Now, I'm going to say one more thing about equilibrium, and we will definitely delve into it more in chapter 3. Equilibrium means the total force is 0. It also means the acceleration is 0. It also means that the change in velocity is 0. If it's objects in equilibrium, if any one of these is true, the other two are true. I am not stating an object is at rest. All I'm stating is that the velocity does not change. And that is definitely a topic for chapter 3, but I at least wanted to put that out there. Part of this is, when I was in 3rd grade, I had a teacher who was talking about finding areas. We did areas, rectangles and triangles, stuff, simple stuff. But then she drew up a curve and talked about finding the area under a curve. And she said, what you do is you divide it up into a whole lot of little triangles. Or sorry, a whole lot of little rectangles, and you add up those. And that confused me, but I thought about it until I took calculus, at which point I went, oh, she was talking about calculus. She didn't use the term calculus. But it was just a little thing that got planted in my head that I thought about on and off for years until the mystery was finally solved for me. So I'm planting a little bug here. We will get back to this. You do not have to wait 10 years to figure out the answer.
Is there a lab like next door
Is it?
for Friday?
It's, if no one is in here, then yeah, we'll be in, I think, 259.
Okay.
If someone is in here, we'll be over there. If no one is in here, I'm taking this room back.
And is that, do you need to turn on the upload to the web?
Yeah, it should be available now. If it's not, somebody send me an email and just send him, I'm not seeing it.
The grafting one, right?
Yes.
Yeah, okay.
Thank you.
So I guess Hannah and Matthew, I assume you're in the Friday lab also.
Yes, sir.
You,
Friday lab?
yeah.
What do you mean?
You're in the section 100 of
We've got the same.
110A.
Okay, then yeah.
Okay. If you go on the blackboard, there should be, I think it's under assignments for 110. go under assignments, and then there should be a subfolder called labs. Click on that, and there should be a lab with the Friday's date, or sometimes I'm off by a day, but somewhere around Friday's date, and something, and it says graphing.
Gotcha.
I want you to print out there's a PDF, which is basically the lab that you're gonna do. Print out the PDF before coming into class, on Friday. If you have printer issues, just let me know,
Yes, sir.
and, you know, we will accommodate, but it's just a whole lot easier if you walk in with it already.
Gotcha. Yes, sir.
Yep. And both of you, welcome to the class.
I do apologize for coming in late. I got so lost, honestly.
You know, first week, it happens.
And I'm sorry I wasn't here Monday. I literally just switched classes from online in person yesterday.
Yeah, and, you know, I appreciate that, it's sort of expected that this happens, you
I
know.
wasn't even enrolled for classes until yesterday. honestly.
Yeah, I was even supposed to be here all semester, and then after Monday, my computer malfunctioned, 5 hours in IT. I'm like, I need the in-person sitting after everything that happened on Monday with the computer failure. It was a nightmare.
Well, I'm glad you made it.
IT definitely knows my name now. Thank you.
Yep. Oh,